Okay, so the first part of this is simplifying radical
This is 5.3.
yeah, 5.3. Okay. 5, 636, 749, 864. Come on. 981, so forth. Okay, so those numbers are going to be important to us again today when we go through this stuff. All right. Let's just do a couple of expressions. First of all, we kind of talked about this already. If we have the square root of 40, okay, and we want to simplify that, then what we want to do is find the largest perfect square that goes into that 40 evenly. Largest perfect square divides evenly. Okay, so there's a list of them right there. Which one's the largest one that goes in there evenly? 4 does. So we have 4 and 10 here. Okay, so there's my perfect square that I can take the square root of, which is 2 is going to go on the outside, 10 is going to stay on the inside. That is what we call simplified. All right, so we've done some of those types of things already. All right, but that's part of what we're going to have to know how to do tonight. Okay, so we want to be able to simplify. If it's a cube root, it doesn't make any difference. It's still the same idea, except obviously the numbers are going to change. So if you have a cube root, of, let's go with 16 for example. Okay, we want to find the largest perfect cube that goes into 16. 8 goes in there and goes in there twice, obviously. So then, what's the cube root of 8?
2.
The 2 comes on the outside, and this 2 stays on the inside. All right, so that's the answer to that one. All right, but the concept is still the same. You're trying to find that largest perfect, whether it's square or cube or whatever the heck is that's on the power of the root that divides evenly. We're going to break it down, and that's what we want to try to do. Okay, so that's part of what we need to know how to do tonight, because to perform some of the operations that they want us to do, that's important to us. So, for example, they have some things where they want us to multiply, all right, each radical expression. So I'm just going to do that. So if I take the multiplication of 6 times the multiplication of 30, all right, how does that work? Well, what happens is you multiply the numbers underneath the square root first. So that's going to be the square root of 180. Does everybody agree with that? We got it right? Okay. Now, radicals are very, very similar to fractions. All right, the rules are almost the same. So when you get done multiplying a fraction, you want to reduce it down. So you're going to do the same thing with this. So then we want to find the largest perfect square that goes into 180. So I go back up to those numbers, and I would say, okay, we want to know what goes into 180. So let's see. I bet 4 does, but we might try 36. I got a feeling 36 might work. 25 is definitely not going to work because that's not. It would be a good guess, but it's not going to work because it's pretty 175. Did anybody try 36?
It's fine.
36 goes in there 5 times?
Yeah.
Man.
Like you're a math teacher or something.
Something.
Wow.
Something, right? So what's the square root of 36?
6.
So 6 is going to come on the outside. 5 is going to stay on the inside. Okay? Now, you might say, yeah, but shouldn't we reduce this 30 down first? Well, you can, but it seems like most of the time it's easier to reduce at the end. All right, your numbers might get big, but it's just kind of a little bit better strategy. See, questions on how we did on that one? What if we had one like this? Let's say I switched it around, put some numbers out in front. So it looks like that. Okay, so we're still multiplying. To multiply these, we're going to multiply the numbers on the inside and the numbers on the outside separately. So a lot like a fraction where you do multiply the tops and multiply the bottoms, it's kind of the same idea. So what are we going to get on the outside of the square root? 6. And what are we going to get on the inside of the square root? 50. And now we have to reduce it. You see, you always want to do that. So when you take your test, whenever that's in a week or so, make sure that you're reducing these square roots. If they can be reduced, what's the largest perfect square goes into 50? 25 and 2. So what's the square root of 25? 5. That 5 comes out, multiplies to that. So what is our answer going to be?
It multiplies into the 6.
To the 6. Yep.
30.
So that's going to be 30 square root 2. Yep. That's how that works.
Oh, I see.
Could you slow down a tiny bit?
Is that what you did?
Yeah, I'm stopping.
Or, can we do another one?
Sure.
Yeah, the square root.
Okay, so the ones that I notice that they like to do a lot of fractional stuff, they just like fractions. Okay, so, and they have here's one where they have a 4th root of a fraction times the 4th root of another fraction times the 4th root of another fraction, like that. Okay, now, if these are something other than 4s, we can't multiply them. You know how? Okay, yeah, that means that we couldn't just, if that's a 4th and a 3rd and a square root, they're not the same. The roots have to be the same in order to just multiply the numbers. Okay. All right, so let's multiply this. So we're going to get the 4th root of, what are we going to get for a fraction on the side of this? 1 over 81. Okay? So now I'm going to treat this as top and bottom. So I'm going to take the 4th root of 1. What's the 4th root of 1? 1. What's the 4th root of 81? I don't think it's 9.
Fourth root of 81
No, it's going to be the square.
Be 3, yep. Yep, it's a 3. Okay. What? No?
I was like 9. I was like,
Oh, okay. So you're good?
yeah.
All right. So that's the answer to it. Okay? So we multiply what's inside the radicals. Okay? And then we could simplify this one, but we don't, it's a perfect 4th of it. So unfortunately, they have a couple of those. Okay? Now we're going to zip over to what?
Can you finish the problem?
It's 1/3. That's it. So you're saying if the,
Fourth and a third and a cube, or a square, or whatever.
so if you're saying if these are different,
Yeah.
Yeah.
well,
You just leave it?
there's nothing, yeah, you can't do anything with that. You can evaluate it using a calculator, but you can't simplify it.
Okay, what if there's like 4 and then a cubed and then a 4? You just do the 4s together?
You
Just
can do
do
the
the two
fours.
that match? Okay.
Okay,
Yeah.
so.
I don't know if you'll see anything like that, though. I mean, I don't think so.
We won't, right?
Okay.
Keep it similar.
Let's see, they have some. Let's do us like this. X to the 5th times. We'll throw some variables in there just to make it different. Okay, so now we have a variable, x to the 5th times x to the 6th. So that's going to be the square root of x to what power would that be? 11, because what are we going to do with the exponents? Add them, right? Multiply and add. Okay. Now, this can be simplified, okay, because we have the square root of x to the 11th. And you can think of this as in a couple of ways. This here, of course, is a 2. So one thing we could do is just come over here to the side and say, if I take 11 and divide it by 2, 2 goes into the 11 how many times? 5. So we're going to get 5 pairs out of that 11. Does that make sense?
Yeah.
Okay. So that means I want to have an x to the 5th on the outside of that. Now, if I have 5 pairs, how many are still left over, though, because there's 11 of them? 1. So that would be the power on the inside. Okay, so you're taking this 11, and we're dividing it by whatever this is. Okay, 2 goes into 11 5 times. That's how many pairs. That's kind of what we were doing right there. X to the 5th comes out. There's a remainder of 1. And that stays inside.
So we can't leave it x to the 11?
My guess is they're going to have you break it down like that.
Or
Where'd you get the 2 from?
This 2, that's the power.
Where'd you get
square.
from?
It's a square root. All square roots are 2s.
Oh, I see, I see, I see.
Yeah, we just never write them.
Okay.
Okay.
So then you divide it. Okay.
So let's try one that's not a square root. Let's try a 5th root, for example. Say we have x to the 8th times the 5th root of x to the 9th. Okay? So that's going to give me the 5th root of x to what power?
17.
17. Now if we use the same strategy and we say, okay, we're going to take this 17 and I want to find out how many groups of 5s I have in there.
3.
Okay, so you're saying 3. So that means that I have 3 x's on the outside, right? And what's the remainder then after I divide that?
2x.
And 2 x's on the inside, and that's a 5th root. I didn't write a very good job of putting a 5th root there. There it is. So again, we took 17, divided it by 5, found out there was 3 with 2 left over. That 2 goes there. That 3 is going right there. Like that's probably the best way to approach it, I think. You just kind of got to divide it. I'm looking to see if there's anything. Yeah. Do we do on page 361 or 360 on yours? Are we doing number 53? Is that one of the ones that is assigned? All right, let's do 53 because that's a pretty good problem. So this is on 362. All right. Problem number 53. I'll change it to red so you can tell the difference, hopefully. All right. And I'm going to try to read this. Let's see. It says the cube root of 8 x to the 6th y to the, is that 5? What's the y power?
3.
3? Okay. and z to the ninth. Oh, good. Okay, so then we're going to, it's a cube root, and we're going to take the cube root of each piece. So each little term here. So what would be the cube root of 8?
2.
2 is going to come to the outside. X to the 6th, so think about that. So 3 is going to go into 6. Twice. Do we have any remainder? No, so I don't have to worry about x's. They're just going to be on the outside. What about the cube root of y to the third is going to be y, and the cube root of z to the ninth is going to be 3. And we don't have any cube root. It's gone because there's nothing to take the cube root of anymore. So that's it. All right, that is it.
Wait, do you divide the cube root by the power? Like the 6 divided by 3, yeah?
Yeah, and that's where the 2 comes from, right? Okay. Yeah, you're just dividing. Okay, so I pretty much did a number of different examples there. Is there any ones on 361 or 362 that you're looking at and you're thinking there's no way I could even attempt to do that one right now? We'll do it. Do you see anything there? No? We're good? You sure? Yeah, go ahead. Sure. Simplify, let all variables be positive, right? Your answer. Okay. So that's the 4th root of 27. The cube root of not.
105.
105. Sorry.
That's okay. Cube root of 9 and 3. Is that what that is? Okay. So here's how we have to do this. All right. Do they want us to simplify this? Okay. 4th root of 27. So then we basically have to know what that is. All right. So I know what it is, but if you didn't, you could try taking the 4th root of 27 like in a calculator. All right. It's probably going to work out. Do you know how to do that part? Because I can show you how if you don't. Yeah, you can do it in Desmos. So I think there's a root thing there with a power. Am I right? I think there is. It might be underneath the It might be underneath the functions.
Oh, in Desmos?
Yeah.
Yeah, it's under functions.
It's under functions.
Miscellaneous?
Miscellaneous. Okay. So what is the 4th root of 27 then? 3. See, now here's an example of where they're all different powers, right? And we can't multiply 27, 9, and 3 because they're all different. So we're going to take each individual one.
The 4th root of 27 isn't 3.
It's not 3.
No, it's
2.287.
Okay. Here's how we're going to have to handle this. We're going to have to find the largest 4th root that goes into 27. Did I sign this problem?
No, I don't think so. I just saw it and I didn't know how to do it.
Oh, okay. I was going to say, I did this? All right. So let's find the largest 4th root that goes into 27. So let's see. I don't know if there is one. Because it has to be 3. 3 times 3. I really don't think there's much you can do with this problem. Because it's 27, 9, and 3, and you can't. It's already pretty much broken down. So they want you to simplify it.
The only thing you can do is
No, you can't really do anything with that because it's a cube root and a square root. Let all variables be positive. Right here, answer in radical notation.
Is it 3?
The only thing I could see is we could write this as 3 to the 1/4 power. Does that make sense? Times 3 to the 1/3 power times 3 to the 1/2 power.
You want to know what the back of the book says?
Oh no, No, I'm sorry, this isn't 3 to the 1/4 power. This would be, I'm sorry, hang on. This is 3 to the 2/3 power. Do you see how come it's 2/3? Because it's 3 to the second is 9.
Okay.
And this is going to be 3 to the 3/4 power.
Yeah.
Okay, and then what would you have to do with all those exponents?
Multiply.
Well, we're multiplying them, but what do you do with the exponents then? Add them. So you got to count the denominators and add them up. That's why I didn't assign it to you. Okay, that's a messy one. But that's what you'd have to do to it. Put that one on the test, huh?
No.
No.
Finish it out.
Yeah, finish it out. And put the answer.
Okay.
That's not what the book says.
Okay, let's see. So 3 to 3/4, common denominator, that's going to be
Give
12. So that's going to be 6 and 8 and no 9. 9, 8 and 6.
wrong.
No, what do you mean wrong? Oh, harsh.
See, you shouldn't even. See, you try to confuse us. Now
23 over 12. Is that what it says?
Nope.
What's it say?
I don't know, but it's
Like 3 to the 12th root.
Yeah.
I got the 12 right?
You got the
It's like
3 right.
on the out,
It's
to the 12th
11.
root, 3 to the 11th. On the
3,
end.
3 11s, 12s.
Oh, well, I just got to reduce that. That's just an improper fraction. You have to reduce it down. Heck yeah. Heck yeah.
You're nowhere close. It's
You
3 to
gonna-
the 12th.
No, we're close. Who's saying that?
Okay, so it's 3
I'm we're close.
you out.
Gosh, I'm way close on that.
The answer it's giving is 3 on the outside. Of
Yeah.
The 12th root of
Yeah.
3 to the power of 11.
Yeah.
You guys, he's someone that's correcting our test. We should double check that.
We can give you points for the part that you got right.
Right, but that's only part.
What did I do?
Yeah, that's partial
To deserve this? What did I do to deserve
You
this?
get partial credit.
Oh my gosh, I want to redo the syllabus again. All right, so we're done. Is there any other ones on there? Or are we good with just that crazy one, huh? Okay, let's keep we'll plug away on this then. 5.4, kind of the same, but now we're going to add, subtract, multiply, divide, all of these crazy radicals. Okay, so we're basically going to do all kinds of operations on them. Operations on radicals. Alright, so again, like fractions, to add or subtract fractions, we have to have common denominators. To add and subtract radicals, we have to have common, there's a word for them, I think they're radicands, but it's whatever is underneath the radical. That has to be common right there. Okay? In other words, it has to be the same. So we could take 3 square roots of 2 plus 4 square roots of 2 and add that to get 7 square roots of 2. But if those things are not the same, so for example, if we try this one, we can't do it. Cannot be done. All right, they have to be the same. So the numbers underneath the radical signs have to be the same in order to add or subtract. All right, very, very similar to what a fraction is like, okay, where you have to have common denominators. So they have to be the same. And it doesn't matter whether it's a square root or cube root or whatever it is, they got to be the same. If they're not the same, can't add them. So if we have 2 square roots of 5 plus 4 square roots of 5, what are we going to end up with there? Square roots of, right. Notice, but we don't add these. Okay, again, very similar to fractions. When you add fractions, 2/5 and 4/5, you don't get 6/10, you get 6/5. All right, so 2 square roots of 5 plus 4 square roots of 5 gives you 6 square roots of 5, not 6 square roots of 10. That would be very wrong. So make sure that we get that. Okay, very, very similar to fractions. We're still adding 2 square roots of 3 plus square root of 12 plus square root of 54. So what we want to do, looks like we can't add these because they're not the same, correct? But we have to break these down. Okay? We're going to break these down and then maybe we can add them. So, what can we break the 12 down? What's the largest perfect square goes in there? 4 goes in that one 3 times. So that's going to be, how can we rewrite that one? Ah, now we can add it. What about the 54? How does that break down? What's the largest perfect square goes into 54? 9 goes in there 6 times. So what does that equal to? 3 square roots of 6. So, what is the answer?
4 square roots of 3 plus 3 square roots of 6.
Exactly. See, we can't add these. We can't add the 3 and the 6 because they're not common. Right? We add the ones that are common. Okay? And we don't add what's underneath there. Don't do that. That would be not good. If they're common, it's great. If they're not, then either reduce them down and get them that way, or okay. Let's see. There's like one like that. They have a cube root one. Yeah, 24. So again, we can't add these, but maybe we can break them down and then we will be able to add them. So 24, we got to find the largest perfect cube that goes into 24. 8 goes in there 3 times. So that breaks down to 2 cube roots of 3. Is everybody seeing that? The cube root. Okay. Plus, now let's see, how about this one? Cube root of 81. So what's the largest perfect cube that goes into 81? That takes a little bit. Well, it's probably a 9. It's probably a 3 thing, right? 20. Yeah.
27
So 27 and 3. Okay. So that's going to look like what then? 3 cube roots of 3. Now we can add them because they're common. So we're going to get 5 cube roots of 3. All right. Do we do 57? Is 57 one of the problems that we do on 373? I don't know what it anything today. Multiples of 3? Oh, 58. Okay. So let's see, we have one like this. 4x plus 8 plus x plus 2. Okay, let's say we have one like this. Same thing. This doesn't look at anything like this. There's no way we can add these. But watch what happens here. We can take this and rewrite it so it's 4 times. If we took a 4 out, what do we get? X plus 2. Alright? So what we did is we took this 4x plus 8 and we took a 4 out. This 4 is common, so we're factoring it out. Now remember that it's a square root, and 4 happens to be a perfect square. So then what's the square root of 4? 2 is going to come on the outside. Look what's left on the inside. And now we can add these. Yep. So we're going to get 3 of them, huh? Yep. There it is. I don't know, because it's not strictly just a variable. If that's called a coefficient. Because mostly those are tied to variables. Yeah. I don't know if it is. Yeah, I did. Square root of 25 x to the 6th minus 36 x to the 6th. So, what are we going to get here? How's that going to break down? 5x to the 3rd, right? Remember, that's a 2, correct? 2 goes in the 6. 3 times with none remaining, right? None remaining. Okay, what about this one? Square root of 36x to the 6th. 6x to the 3rd. Oh, now we can figure this one out. 5x to the 3rd minus 6x to the 3rd. Negative x to the 3rd. So the bottom line is, as long as the numbers inside the radicals is the same, you can add and subtract them. Okay, but you can't if they aren't. Okay. Let's multiply, and then I'll give you a quick little break here. Multiply. Let's start simple here. Well, I guess we already did that, right? We multiplied these kind already, right? Yeah, we did that in the beginning. Okay, let's do this then. 2 minus the square root of 3 times 4 plus the square root of 5. Alright, we'll do one like this, and then we'll make a simpler one. Okay, so, guess what we're going to do here?
Foil.
Yep, we are going to FOIL. Okay, so, FOIL, 2 times 4, 8. 2 times that. What do you think that is? 2 square roots of 5. Very good. We do not multiply the number on the inside with the whole number like this. Okay. Just because we're at 5. Minus. What about those two? 4 4 square roots of 3 minus, what is this going to give us? Which is square root of? Yeah, multiply, what do you get? 15. Okay. Can we break the square root of 15 down? We can? I don't know any perfect squares going to 15. That's done. Alright, can't do anything with it. Done. Can't break down to 5, can't break down to 3, can't break down to 15. That's all I can do. Okay.
Yeah.
Yeah, because they're both underneath. That's okay. Very much like a fraction. Okay, so now let's say we have something like this one. We're going to FOIL again because that's how we multiply. So I'm going to FOIL here. 3 and 2, what's that going to give us? 6. I was writing perfect. 6. And then I have 3 there, so that's going to give me 3 squared is 10. I didn't want to write green, but anyway. Then I'm done with that one. So now I go this way. 2 square roots of 10, yep. And now I'm going to go this way. Negative square root of 100 or 10. So we have 6 minus 3 square roots of 10 plus, I'm writing this all out, 10 and 100. So what is this all going to simplify down to? Yep. So we take the common number, this one here, that's common. These two are common. And then we get our answer. And that's how you're going to multiply them. Sure. So, did you understand the this one? Okay. And so the square root of 100 is 10. So now we're going to add the common thing. So we have a 6 and a 10. 6 and 4. So these two together, so a negative 3 plus a negative 2, those are common. Yep. Do you see that? So, 3 square root of 10 plus 2.
Imagine instead of looking at that square root of 10, look out at the back.
Yeah.
So negative 3x plus 2x.
That is correct. Yeah. It's the same as the next two. In that case. We can do another one here. So let's go with 2 minus the square root of, I'll use 6. 6 is a good number. 6 times 3 plus the square root of 6. So a FOIL. I guess I kind of did this one already. Well. So what's that going to give us? 6 plus 2 square roots of 6 minus 3 square roots of 6 minus square root of 36. Right, so now we have 6 plus 2 square roots of 6 minus 3 square roots of 6 minus 6. So now we're combining our like terms, right? Oh, look at that. They cancel out. What are we left with? Negative square root of 6. Yep. Okay. But you're just spoiling. Stanley made a good point. He says, well, you can treat the square root of 6 as like x as you can. Yep. Very much the same. You just don't want to combine what's underneath there and get 12. That would be bad. Questions on the multiplying. We added, subtracted, simplified, multiplied. Oh, sure. I like this.
You're gonna have so many cookies for Texas.
I got some at home, actually, yeah.
Oh, well, why? You don't need
They get eaten. All right, go ahead, take about a 10-minute break. We'll come back and do some divisions. I want to get this load up so you can check your grade things here. We'll be done pretty shortly. That's about all I can take anyway and get ripped on here. Let's see. Thanks,
Can I still turn in late work, or do I have to
Yes.
wait till Monday?
you can.
Right now, or do I have to
Yes.
wait till Monday?
No, you turn anytime you want. Set it right there. Yeah, we take that.
For you too.
Huh?
I got a little present for you.
Oh, I like. Let's see what it is. Okay. Who wants to be first? Do you know your GO number? Need your GO number.
My student number?
Yeah, whatever that GO number is.
Do hers.
Okay.
Zero, three, 3789125.
Oh, that's it? All right. So page 90 and page 114, I don't have that. I don't think they sign it. Okay. If I'm guessing that might be the second one that we did, it looks like, the second assignment. Okay, we'll show it, but you can check and see what the second one is.
Page 90 and 115.
Yeah, that won't right. In my briefcase, just go ahead, there's nothing.
I'll
in there.
remember.
Are you sure? You want me to reach in and pull that?
Probably in there somewhere.
Oh my God, calm down.
All right, here we go. So let's do some more people if I didn't get you for sure before we leave. All right, last thing we're going to do is divide these, but this is better known as rationalizing the denominator. Yes. D-N-O-M-I-N-A-G-O-R. Okay. So the basic rule is no radicals in the denominator of a fraction. Okay. No radicals in the denominator. Can't have that. I don't know why, but it's one of those mathematical rules. Okay? No radicals in the denominators. So what that means, if we have 2 over the square root of 12, all right, we can't have that down there. So what we're going to do is, it's called rationalizing, which comes from the idea that we're going to make that square root of 12 a rational number rather than an irrational number that it is, by simply multiplying by the square root of 12. All right, so that's what you do. So now the bottom's going to be simple. So the square root of 12 times the square root of 12, what's that going to be? And what are we left with? Just 12. right? Square root of 12 times the square root of 12. Square root, if you don't like what we did there, that's the square root of 144, right? Multiplying the numbers underneath. Square root of 144 is 12. Okay, so this way to this way. I haven't done that part yet. Okay, now on the top, we're going to get 2 square roots of 12. Okay, because you can't multiply the 2 and the 12, right? Because there are 2 and then 12s underneath, so you can't multiply them. Now, this can be reduced, right? Because it's like a fraction, so it can be reduced. A couple ways we can reduce it. I think I'll do this first. So that 2 is going to reduce, and the 12 is going to reduce. So I get the square root of 12 over what? 6. Am I done reducing?
No.
Nope. What else can be reduced?
You could put a whole, or 4, 3.
That's right. We can reduce this down to, right, to 4 and 3. So square root of 12 can be broken down into 4 and 3. So, oops, here we go. So now we have 2 square roots of 3 over 6. Oh, I can reduce that again. Square root of 3 over 3. Alright. So that's called rationalizing the denominator. You cannot have a radical in the bottom of a fraction. But it's not too hard to get rid of. You just got to multiply it basically by itself. So let's try another one. Same thing. So let's go with 4 over the square root of 20. Okay. So again, I'm going to rationalize this. So what are we going to multiply by? Square root of 20. Square root of 20. That's good because what do we get on the bottom? 20. See, so that's great. That's what we want. We don't have a square root down there anymore. But we have one on the top. We'll just kind of reduce stuff. What do you want to do first here to reduce this? 4 and a 20. Okay, so that's going to give me what on the bottom? 5. And what on the top? Square root of 20. 1 square root of 20. Yep. Good. Are we done reducing? Nope. What can we reduce down now? Square root of 20. So let's see. That breaks down to, right, 4 and 5. So that would be 2 square roots of 5 over 5. And we can cross those 5s out, right? No, you can't. Good deal. You leave them alone because one's a radical and one is not. Right? So you can't cross those out. You were about to get confused?
Yeah, I was like, oh, we didn't do that for long.
I know it. Yeah. Okay, can't do that. Leave them alone. Alright. How far are we going on those? We don't go into 107s, 108s, right? You know how far we're going? On page 373, 374. 102 is the last one? Okay, that's good. Alright, let's do kind of one like that then. Let's see, we have 3 over 2 square roots of 5. Okay. So, now we have a little different, but kind of the same idea. What do you think we're going to multiply top and bottom by? Do we need to multiply by the 2? What are we trying to get rid of? Then let's just multiply by that. Okay. We don't. You can multiply by 2, but you don't have to because we don't. It's okay. We just want to get rid of that 5. That's the thing's messing us up. So the top's easy. 3 square roots of 5. What are we going to get on the bottom? Very good. 10. Where's the 10 coming from? Yep, we got square root of 5. Square root of 5 is 5 times that times 10. Okay. Can this be reduced? That's done. We can't reduce it. Okay, we can't reduce it. anything on that page or anything that we've done on 373, 374, any problem there you want to see done before we take our quiz? Anything in there, don't hesitate. Okay, if you didn't check your grade then before you leave, you should. And then, if there's something, anyway, you should. Okay? You should check it. So, Ron, I'll go and check at some point within the next week or so. We need to straighten it out. Okay? But I'd rather do it now than. Okay.
Because I have all of my assignments.
Okay. So, and if you want to wait to the, you can wait to the very end of class. That's up to you. I can't.
Sure you can. People love that. Yeah.
So I do have some stuff with no names on
My
it,
wife always.
but I don't know if that was one of them.
I don't think it's forgotten.
I would bet it doesn't have the color.
You think it's just a handwritten
I
thing?
think so.
Yeah, no. That's why I'm not really.
I don't think I ever went to high When was that?
I still believe that because my
At 22 or something, yeah. Yeah. I'm sure I'll spend time to all more stuff. He doesn't have to watch it all day.
Yeah.
What is that? I was wondering on Friday.
like that's exactly how we thought.
What are you trying to do with John? Yeah, I'm probably gonna work.
Well, no. They're chopping it like this. They're chopping it like this.
No.
Oh,
But I have it on my phone.
Feel better?
Oh yeah.
You look a little rough, money.
hang on up, I need this.
I know that. Not rough and then rough.
Yeah.